Across the world, shopping malls are becoming empty. Large buildings, prime locations, quiet corridors where people used to gather. At the same time, demand for data centers keeps rising. More data, more computing, more infrastructure, everywhere. When you put those two facts side by side, the idea almost suggests itself. If we already have big, empty buildings, and data centers need space, why not reuse them? A shopping mall already looks like a ready-made solution. It has large, open floor areas designed to handle crowds. It already has electrical supply, lighting, and distribution. It has access roads, parking, and utility connections built in. From the outside, it feels efficient, even responsible, to reuse an existing building instead of constructing something new. This way of thinking feels practical, it feels economical, and it feels like common sense. But common sense is shaped by how buildings work for people. Data centers are not designed around people. They are designed around machines that run continuously and are never allowed to fail. And that difference changes everything.
This is the point where we deliberately stop and change the question. Most conversations immediately focus on how a shopping mall could be converted, how to upgrade the power, how to improve cooling, how to rearrange the internal space. That approach feels practical, it feels technical, and it feels productive, but it quietly assumes something important, that conversion is the right objective to begin with. Instead of asking how to convert a mall, we should ask why experienced data center operators almost never choose to do this at all. That shift in perspective matters, because when you start with the right question, the answer tends to reveal itself, even if it's uncomfortable.
The most serious problems don't show up on the surface. They don't appear in marketing brochures, they don't show up in real estate listings, and they're rarely visible during a casual site visit or walkthrough. They exist in places most people never think to look. Structural loading limits that were designed for crowds that move, not machines that sit still. Electrical systems meant to distribute many small loads widely, not concentrate massive loads in one place. Airflow paths designed for human comfort, not continuous heat removal day and night. And building layouts that allow problems to spread, instead of isolating failures when something goes wrong. A shopping mall was engineered around people, how they enter, how they circulate, and how they leave. A data center is engineered around machines, how they operate continuously, how they generate heat, and how they must keep running even when parts of the system fail. These two design philosophies are fundamentally different, and most of these differences remain invisible right up until the moment something breaks.
Let's talk about something simple but completely unforgiving. Weight. Server racks create heavy, concentrated point loads. They don't move, they don't shift, they sit in exactly the same place every hour of every day for years at a time. Shopping mall floors were designed for people. People walk, pause, gather, and then leave. Their loads are dynamic, spread out, and temporary. Data center loads are fundamentally different. They are static, they are continuous, and they are concentrated into relatively small areas. Once a building is constructed, its structural limits are largely fixed. You can reinforce small sections, add steel, or thicken slabs locally, but you cannot easily change the original load paths without invasive and expensive reconstruction. If the floors are wrong, every other system is forced to work around that limitation. In data centers, the floor is not just a surface you build on, it quietly defines what is possible and what will never be.
Power is often misunderstood. Most discussions stop at capacity, how many megawatts a building can receive from the grid. But in a data center, power is not just about quantity, it is about geometry. Where the power enters the building, how far it must travel to reach the IT load, how evenly it can be distributed across halls, and how redundancy is physically separated, not just drawn on a diagram. Shopping malls were designed to spread power out. Many tenants, many small intermittent loads, long distribution paths that were never meant to carry dense, continuous demand. Data centers work in the opposite way. They concentrate very large, continuous loads into very specific zones. Redundancy is planned spatially, with clear separation between normal paths and backup paths. If rooms are in the wrong locations, if distances become too long, or if redundancy overlaps where it shouldn't, reliability slowly erodes. In data centers, power works best when the building geometry supports it, not when the geometry quietly works against it. Cooling is even less forgiving than power. Air does not care about intentions, drawings, or assumptions. It follows pressure, temperature, and geometry, nothing else. Shopping malls were designed to keep people comfortable. Air is supplied broadly, mixed freely, and allowed to circulate. Small inefficiencies don't matter when people come and go. Data centers operate under very different conditions. Heat is generated continuously, in very specific locations, at levels far beyond human comfort. Cooling in a data center depends on precise airflow control. Cold air must reach equipment directly. Hot air must be captured and removed predictably. Any mixing reduces efficiency and increases risk. In retrofitted spaces, air takes shortcuts. It leaks, recirculates, and mixes in ways that are hard to control. Physics always wins. And in data centers, cooling problems rarely fail loudly. They fail slowly, quietly, and expensively. This leads to a principle that experienced data center operators understand very clearly. In data centers, early decisions are extremely difficult to reverse. Once systems are installed and equipment is live, structural changes become invasive. Power changes ripple across multiple layers of redundancy. Cooling adjustments affect airflow patterns throughout the entire space. What may look like a small compromise during design often turns into a permanent limitation during operation. Every correction takes longer than expected, costs more than planned, and carries far more operational risk than anyone is comfortable admitting. Unlike offices or retail spaces, data centers do not allow gradual experimentation. They operate continuously. Downtime is expensive, and even short disruptions can have consequences far beyond the building itself. That's why experienced operators are cautious early on. In data centers, mistakes don't fade with time. They accumulate and they compound. This is the reason data centers are almost always built new. Not because operators enjoy spending more money, and not because they overlook existing buildings. They build new because purpose-built facilities allow failure to be controlled before it ever happens. Load paths are designed intentionally, not inherited from past uses. Power rooms are placed where they must be, not where space happens to be available. Cooling systems are integrated into the building itself, not added as an afterthought. And redundancy is planned spatially, so backup systems remain truly independent. In a purpose-built data center, when something fails, it fails in a predictable way. The impact is contained, and the rest of the system continues to operate as designed.
This level of control is extremely difficult to achieve in retrofitted buildings. This isn't about convenience, speed, or aesthetics. It's about engineering for failure, because in data centers, failure is not hypothetical. Purpose-built facilities exist because some risks are too costly to discover later. So, can a shopping mall work at all? The honest answer is, sometimes. A mall can host computing equipment at relatively low power density, it can support non-critical workloads, and it can be suitable for short life cycle, transitional, or experimental use cases. But this is very different from what most people imagine when they use the term data center. When people think of a data center, they usually picture dense compute environments, high availability requirements, and infrastructure that is expected to run continuously, day and night, without interruption, for years. Those expectations place very specific demands on structure, power delivery, cooling behavior, and redundancy. They assume failure has already been designed for, not reacted to. Most existing commercial buildings were never engineered with those assumptions in mind. So yes, a mall can host servers, but hosting servers is not the same thing as being designed from the beginning to operate like a data center. Now, let's step back and look at the idea from a different angle. What if the shopping mall was never meant to be the data center? What if its role is downstream, supporting the ecosystem around the data center, rather than hosting the critical infrastructure itself? Shopping malls are designed around people, movement, accessibility, daily interaction. They are built to handle flow, coordination, and routine activity. That makes them naturally suited for roles like offices, operations and support teams, training facilities, logistics coordination, spare parts storage, and day-to-day administrative functions. These functions are important. They keep organizations running smoothly, but they do not need to be mission-critical or fault-tolerant at the infrastructure level. Meanwhile, the actual compute infrastructure, the part that must run continuously, that must tolerate failures, and that cannot afford uncertainty, can live in a purpose-built facility designed specifically for that role. By separating people from machines, you reduce operational risk, simplify system design, and allow each building to do what it was originally designed to do, and do it well. So here's the uncomfortable question. If converting shopping malls into data centers is so risky, why does anyone still try? Cost pressure is part of it. The desire to move quickly is part of it. And sometimes the optics of reuse feel hard to ignore. On paper, it can look cheaper. On paper, it can look faster. And on paper, it can look like the responsible decision. But infrastructure doesn't respond to intentions. It doesn't care about good ideas or good motives. It responds to physics, to geometry, and to limits that don't negotiate. This question isn't meant to be answered yet. It's meant to slow the conversation down and make you pause. If empty buildings don't work the way we expect, then the real question becomes even more fundamental. What actually determines where data centers are built and how big they are allowed to become? Why do some data centers grow massive and centralized, concentrating enormous amounts of compute, power, and operational risk in a single location, while others move deliberately towards smaller, distributed designs spread across regions? Is that decision driven by power availability, by network latency and connectivity requirements, by land cost, regulation, and planning constraints, or by the consequences of failure when something eventually goes wrong? And how much risk is an organization truly willing to concentrate in one place versus how much operational complexity it is willing to accept by spreading systems, teams, and infrastructure across many sites? These choices are never accidental.
They reflect real constraints, real trade-offs, business priorities, and an organization's tolerance for failure. Once you start seeing those forces at work, the size, shape, and location of data centers stop looking random. That's the question we'll explore next.
This discussion isn't about rejecting ideas, and it's not about saying reuse is always wrong. It's about understanding roles, constraints, and consequences before decisions become permanent. When it comes to critical infrastructure, the building itself matters less than what you ask it to do and what you expect it to tolerate. So before you build forward, pause for a moment, question the assumption, and think sideways. Thanks for watching.